So last lesson we talked about logarithms and introducing ourselves to what a log is. This time we're going to be using logs in order to solve exponential equations. All right, so our focus here is basically on solving exponential equations. And we're going to do a little bit of the change of base formula. So for logs. So our goals are to be able to use this change of base formula to evaluate logs and to solve exponential equations. So let's talk about the change of base formula because it's something that was mentioned last class when we talked about logs. So last class we talked about the common log and the natural log. So the common log, remember, has a base of 10. So this guy right here, you should be able to calculate that. That's log base 10 of, whatever, you're doing it for. And this is the log base E of whatever you're doing it against. So this is the natural log and this is the common log, but however, the calculator doesn't have anything for bases other than 10 and E. It only has the log and ln key. So how do we calculate logs of different bases? Well, if you want to calculate logs of different bases, this is why we use the change of base formula. All right, so it's real simple. All you have to do is take the log of the big number divided by the log of the small number. So the log of the big number divided by the log of the base. And you can either do this for the common log or you can rewrite it as the natural log. It doesn't matter which one you use as long as you use the same one throughout. Okay, so you have to either use both natural log or both common log. And this is how you would do it on the calculator. So let me show you. So if you wanted to do log base 3 of 5, well, you can either do the common log of the big number, 5, over the common log of the base, or so you could say, or this also equals, so I'll just say, here, let me erase that. So I can say, or you could write it as the ln of 5 over ln of 3, and they will give you the exact same number. So we're going to quickly calculate that number. Again, these the log and the ln keys are already in the calculator built in. So you would get 1.465. All right. So again, with this one, you're going to do the log of 20 over the log of 5. Or you could do the ln, and you would get the same exact answer. Right, and you get 1.861. All right, this one you can't actually evaluate it, you can only rewrite it, okay? So we're going to rewrite this as log of x over log of 5, and that's the only thing you can do with it since x is not a number, so this is all you can do. So we'll just leave it rewritten like this. All right, so this change of base formula you can imagine is really useful if you need to calculate logs of different bases, which occurs more often than not. So let's look at solving exponential equations. So with solving exponential equations, there are a couple of different types, essentially. The first type of exponential equation, you can generally find the answer by using your exponent property, so using exponents. And the second type, there's no way that you could do it in your head, and there's no way that you can do it with knowing your exponent properties. So we use logs for that. All right, so let's look at the first type. So solve the exponential equation for x. So what we do here is, since we want to solve for x, and we have noticed that we have a 5 here and a 125. Well, if I know my exponent properties, I can rewrite this as, I can rewrite the 125 as 5 to the third power. And the reason I could do that is because, 5 to the third is 125. 5 times 5 times 5 gives you 125. And if you don't believe me, just do that on the calculator. You're going to get 125. So the reason why I do this is I now have the same base. You see that I have the same base. And so then I can rewrite this. So I have 5 to the x plus 2. And I have now, since I have a power raised to a power, I multiply those. So I multiply them. And now since I have the same base, what I can do now is set the exponents equal to each other. Since the bases essentially cancel out, now you can set the exponents equal to each other. And this simplifies the problem immensely. So now we can go ahead and proceed to solve. So I'm going to subtract x on both sides. So I have 2 equal to 2x, divide by 2 on both sides. So I have x equal to 1. Then if I plug that in, I get 5 to the third power equals 125 to the first power, which makes sense. All right, so let's show you how to do this one. So here we want to make sure, we want to see if the base 32 can be rewritten as a base of 2. All right, well, I know that 32 is 2 times 2 times 2 times 2 times 2, or 2 to the 5th. So I can rewrite that as 2 to the 5th. So I got 2 to the 5th, and then in parentheses, and then I got the x minus 1 power there. So now they have the same base. Don't forget that you're going to multiply these. Power raised to a power, you're going to multiply or distribute that. 5. So we have 2 to the 4x. And this is the part that you got to be careful with the distributive. So you got 5x minus 5. Now we have the same base here. Let me rewrite this because this is a big 2. We have the same base. So that means we're going to set the exponents equal to each other. So we have 4x equal to 5x minus 5. All right, so I'm going to subtract the 5x on both sides. So I get negative x equals negative 5, which means x equals 5. All right, let's look at another one. So in this example, we have to isolate the exponential part of it. So we need to get rid of that plus 3, all right? So I'm going to get rid of the plus 3 by subtracting 3 on both sides. All right, so now I know that I can rewrite 25 as 5 squared. And then now I can set the exponents equal to each other. So I know that x plus 2 equals 2, so that means x has to equal 0. And there's my final answer. So these are type 1 equations. These are ones that you can do if you know your exponents, and then you can set the exponents equal to each other and solve. So the second type is type 2, is the second type, and with this kind, you can't necessarily use your exponent. So this is where the logarithms really shine. So remember that the exponential function and the logarithmic function are opposites. They're inverses. They cancel out. So to cancel out the base of an exponential function, you need to take the log of both sides with the same base. So for example, if you had 2 to the x equals 5, well, the only way you can get rid of that 2 is if you did a log base 2. So you would have to do like log base 2 of 2 to the x. Whatever you do on one side, you do on the other. All right, so do the log of both sides there. And then now these will cancel. And then it leaves you with x equals log base 2 of 5. Okay, so just an example of how you would do that. All right, so solve the exponential equation for x. So again, we have 4 to the x equals 15. So in order to get rid of that 4, I need to do the log base 4 of both sides. All right, and now you can see that the log base 4 cancels out with the base of 4 there. So we have x is equal to log base 4 of 15. All right, and then remember, if we want to calculate this, we can now calculate this using the change of base formula, which is log of 15 divided by log of 4. All right, so if they want you to find the exact answer, then you can write it as this answer or that answer. But if they wanted you to find an approximate answer, then that means you'd have to actually do it on the calculator. So if you wanted to do an approximate answer, then we will do this on the calculator. All right, so we're going to go ahead and calculate this. All right, and I got 1 point, and I'm going to round to three decimals. Usually they'll tell you what to round it to if they want to approximate, but we'll do 3 decimals, 1.5953. Or if they want the exact answer, you can use that, or you can use that. Depending on, you can use either of these for the exact answer, or you can use the approximate answer depending on what they're asking about. All right, so we're going to do the same thing. This is similar to the one that we solved before. So we got to subtract the 3 on both sides. But see, now this one gives you 22. It no longer gives you 25. So this is not a type 1. This is the second type. So I got to get rid of that 5. So I'm going to do the log base 5 of both sides. So now those cancel. So I have x plus 2 is log base 5 of 22. And then now I can subtract. I need to solve for x here, so I need to subtract 2 on both sides. Again, you cannot subtract the 22 and the 2 here. The log base 5 of 22, it's all one thing. They come as a package, okay? You can't separate those two from each other. So you can't subtract the 2 there. So we're just going to literally write it as log base 5 of 22 minus 2. All right? And if you wanted to calculate this, then again, you're going to use a change of base formula. So log of the big number divided by log of the base, and then subtract 22. All right, so that's the exact answer, or if you wanted to approximate it, we can get an answer for that. So I got negative 0.079. All right, so now let's do this one. So again, we got to get rid of the 13, so we're going to subtract that on both sides. So now we got 6e to the negative 5x equals 2. We got to get rid of that 6, because remember, our goal is to solve for x. But before we can get rid of the e and all that, we need to get rid of the 6. This reduces to 1/3, just a fraction. Now, how do I get rid of the e here? Well, the only way to get rid of e is to do the log base e, or the natural log. Remember, the natural log is the same as the log base e. So I'm going to do the natural log of both sides. And now the e's will the natural log and the e will cancel. All right, now we can divide by negative 5, and we get our exact answer. So that's our exact answer. And then if you wanted to do it as a decimal, we can. You get 0.220 approximately. All right, and then that's how you solve for x in those types of equations. Also, keep in mind that even though we solved the first type of equation without the use of logs, you can still use logs. It's not like with the first type you don't, you can't use logs. You can still use logs and get the answer. So I'm going to show you how to do that real quick in number 4. So these are the same exact equations as on problem number 2, but this time we're going to use logs. So to get rid of the 5 here, I need to do a log base 5 of both sides. All right, so now the log base 5 here cancels. So I have x plus 2 equals log base 5 of 125 to the x. All right, and then you'd have to figure out what log base 5 of 125 to the x is, right? So you'd have to figure out what log base 5 of 125 is. But, you know, so you can figure out what log base 5 of that is, of 125. So let's kind of do that off to the side, all right? So that way we can show you. So log base 5 of 125 to the x equals a variable. I don't know, I'll use y. So we have 5 to the y equals 125 to the x. All right, so what is going to give me this? Well, if I know that this is 5 to the third, then I know that this is going to equal to 3x. And then I can replace this with 3x. All right, and then I can solve, you know, per usual, and then just solve it, just like we did before. Okay. So yeah, so I mean, you can always use logs for that, but you don't have to. All right, for these types. Again, so we'll do this one. So log base 2 of 2 to the 4x. The only way to get rid of that 2 is to do a log base 2 equals log base 2 of 32 to the x minus 1 power. So we have 4x equals, so now what we could do is we could rewrite 32 as 2 to the 5th power. And then of course we have the x minus 1 next to it. And then now the log base 2's cancel. You see this 2 in the log, they cancel, and it gives me the exact same thing that I had before, which is the 5 times x minus 1, and then I can proceed to solve it. All right, we solved it the same way that we did before in problem number 2, so just look at that. All right, and then for this one, subtract 3 on both sides. Now we could do the log base 5. So those cancel. So we have x plus 2 equals log base 5. Now we can rewrite this as 5 squared, and then the 5's cancel. So yeah, x plus 2 equals 2, and x is equal to 0. So there are a couple ways that you can do this. So I'm showing you multiple techniques, just in case you remember one or you favor one over the other, right? But they all essentially mean the same thing. They all revolve around the same concept of exponents. Okay, so we can use logs to help us solve exponential growth and decay problems, or compound interest problems for the variable time. So before, when I told you we haven't learned how to find the x-intercept, or we haven't learned how to find the time, now is the time that we can find it. No pun intended there. So for the following problem, we want to solve for time after how many months. All right, since we are trying to find time, and they tell us the population is 34,000. It's decreasing 5%, so this is a decay type of problem. After how many months will there only be 5,000 people left? So we have y. Remember the model is y equals a 1 minus r to the t power. So the r is 0.05. That's our a. And in this example, this is our y. The 5,000 is our y. So we have 5,000 equals 34,000 people in the beginning. So I'm going to do the 1 minus r now. So the 1 minus r part, that's 1 minus 0.05, which is 0.95. So I'm going to do that first and then plug it in there, okay? That way I don't have to show multiple steps here. So I got 0.95 to the t power. All right, so we are solving for time. We're solving for the exponent. In order to solve for the exponent, we need the log, because the log gives us the exponent. So I need to solve for t, which means I need to get rid of the outsiders first. Get rid of the 34,000. All right, the zeros here cancel. So we have, this is 5 over 34. All right, and that cancels. All right, so we got 5 over 34 equals 0.95 to the t power. All right, well, how do we get rid of the 0.95? Well, we need to do a log, more specifically a log of 0.95. All right, so that'll cancel. So now the 0.95s cancel, and then I get my t. So t equals log of 0.95, or log base 0.95 of 5 over 34. And I can do that on the calculator. Remember the change of base formula? So log of 5 over 34 over log of 0.95. And I will get my answer. So I get 37.4 months. So it would take that long for the population to decrease by to 5,000 people, right? All right, so bacteria in a dish grows at a continuous rate of 14% per hour. If there are 10,000 cells now, when will there be 10,000? Okay, so this should not say 10,000. This should say 100,000. So make sure you change that. So there's 10,000 cells now. When will there will be 100,000? All right, so we get the rate is 14% or 0.14. So we got y equals a, and this is a growth continuous rate. So we have 1 plus, or this is a continuous rate, sorry. This is continuous. So since it's continuous, we are basically, this is continuously compounded essentially. So continuous. So remember, continuous is PERT. A equals PERT, P-E to the RT. So that's the equation that we're using for continuously compounded or continuous rate. All right, so therefore we have, so this is, we have P, that's P, this is A, and we got our R. So we got 100,000 equals 10,000 E to the 0.14 times T. So now we're solving for the time. How long will it take for that to happen? So we got to get rid of the outsiders first, get rid of that 10,000. So those cancel, so 10 over 1 is 10. Those cancel. So you have 10 equals e to the 0.14 t. So the only way to get rid of e is to do the ln on both sides. So I'm going to do the ln on both sides. All right, so that cancels. So now we have ln of 10 equals 0.14 t divided by 0.14 on both sides. So t is equal to that. And then we can get what that answer is. So we have 16.45. So 16.45 hours, since we are doing it per hour. So it'll take less than 24 hours, so less than 1 day for the bacteria to grow tenfold from 10,000 to 100,000 cells. That's a pretty quick amount of time for it to grow that quickly. But that's generally how bacteria tends to grow. They tend to grow exponentially. All right, guys. So that is it. I hope you found this useful, and I will see you guys next time.